here we have a problem with centrifugal force and friction. So let's draw a diagram and see what's going on. I'm going to start with the top view of the situation. So this car is going around a circular track of radius 45 meters. And, the car at any given point, it starts with no initial velocity, and it has a tangential acceleration of 2.5 meters per second squared. And let's see, the forces acting on it, you got centrifugal force, which points radially outward, and the only thing holding it in place has to be static friction. Now if we look at a side view of the car, as the car goes around the track, so here's the car, and then here's the little track that it's on. We've got a normal force which points up, gravity that points down, centrifugal force that points radially outward, and static friction that points radially inward. Okay, so let's read the problem here. So it's accelerating tangentially. Let's see. We want to know how many seconds does the car move until it skids off the track. So we're going to have, I guess, well, one way to write this, I can think about this in linear sense, that delta S is equal to something V naught, V, A, and T. So I can write it like this, that the initial velocity is 0, and the angular acceleration is 2.5 meters per second squared. And I don't know the final velocity, I don't know delta S, and I don't know time. Or I could consider the angular displacement and so forth. Looking at the angular quantities, it has an initial angular speed of 0. The angular acceleration is the tangential acceleration divided by r, the radius, so that's 0.0556 radians per second squared. Okay, so either way you want to look at it, I'm trying to find time. I'm trying to find how long this thing moves. So I can get that if I either find the displacement or the velocity, angular displacement or angular velocity. Now, we're told that the car is moving until it skids off the track. So when the car is right on the verge of leaving the track, right before the car skids off the track, at that moment we're at a threshold, so the force of static friction is equal to its maximum possible value, which is mu sub s times the normal force. Right, so at that moment, the sum of all radial forces is positive mv squared over r, because the centrifugal force points out, and then minus mu sub s times the normal force, because the force of static friction points in, and those add up to 0. Now, the normal force in this case, if I just look at the sum of the y forces, the normal force is just mg. I guess I kind of neglected my sign conventions here. Radially outward is positive, up is positive. That's how we usually do it. So, let's see, I got mv squared over r minus mu sub s mg is equal to 0. M can be divided out of all terms, right, because 0 divided by m is still 0. And so I'm left with v squared over r is equal to mu sub s times g, or v is the square root of mu sub s times g times r. Now mu sub s is 0.75, g is 9.8, and r is 45, so that works out to be 18.19 meters per second. Now that's how fast the car is going right before it skids off the track. So, I've got that. If you'd rather do it in an angular sense, then you could say that omega, the angular velocity at that moment, is that. All right, so in order to find time, I'll use this set of equations to find time. I'll use the equation that doesn't have delta S in it, which is this one. So 18.19, 0 plus 2.5t. Right, notice that I'm using the tangential acceleration here, not the centripetal acceleration. So I get time is equal to 7.3 seconds. You could do the same with the angular quantities. You could say omega is equal to omega naught plus alpha t and solve for t that way and get the same answer.